So in my opinion, so I've been coming to IPAM since 2005, and since 2005, and even before, there were programs on trying to solve and address quantum mechanics of material science, biology, chemistry, and so on. And so looking at this progress, right, how much we have achieved, well, I think we have achieved a lot in terms of method developments and applications. But if you look at the size of the systems that we can study, I don't think we have progressed so much, really, from 2005. And so I think what is missing a bit is a bit more fundamental understanding of how quantum mechanics emerges. And quantum mechanics emerges really from the quantum vacuum. So in my view, we need to understand more about the interacting quantum vacuum and then understand how atoms, dimers, and larger systems really emerge from the definition of a very general quantum vacuum state, which is a system with an infinite number of degrees of freedom. So what I would like to do then is I will not progress in the way that I put my title from vacuum to atoms to engineering scale structures, but instead I will actually start with engineering scale structures. I will give experimental evidence of non-trivial quantum mechanical effects that influence structure, dynamics, and stability of large systems at the engineering scale, nano and mesoscale in this case. And I will proceed towards vacuum, so what we can understand about vacuum and how then we go then again to atoms and finally to engineering scale structures back. Okay, so let me start with experimental evidence. So here is one particular experimental study, 2014, by Rodney Ruoff and Ken Lichty, who are quite prominent material scientists or nanoscientists. And so the title of this paper is Ultra Long-Range Interactions Between Large Area Graphene and Silicon. So what is done here is you have the system, which is an interface. You have silicon on both sides. You have this epoxy, which is a glue, and you glue graphene to this interface, and then you insert a plastic wedge which delaminates graphene from silicon. And what you can do is then, as a function of the separation distance between silicon surface and graphene layer, it's a single graphene layer, you can measure the adhesion force, right? And the question is, when this adhesion force vanishes to zero. So if here the interactions are just given by electron correlation of Thunderweight interactions, and for that reason you would assume, based on density functional theory calculations with empirical Thunderweight potentials, that the decay should happen at a few nanometer scale. Okay, but if you look at experiments, here are two experimental curves. There are different curves. There are three curves in that paper, but they all indicate that the interaction decays very, very, very slowly. And I'm cutting this off here because that's what we published, that's what we could calculate. But if you look at the experimental curve, then the adhesive stress in megapascals here does not decay to zero until about 2 micrometer separation between the graphene and silicon surface. So this is really ultra long range. And of course, experimentally, they cannot explain why this is so ultra long range. So this is really 3 orders of magnitude more than you would expect from simple first principles calculations based on density functional theory. And so we decided to study this, and this is really, it's a macroscopic structure, it's an engineering scale structure. We cannot study this in full detail. And so what we do is we just select a part of the system. In this case, we model it as 2 coupled chains, right? Which is, of course, quite a huge approximation. But these chains have a length of 2 micrometers each. So you have 20,000 atoms in each chain. And we do the simplest possible model for the chain, right? So in this case, the interactions are chemical interactions plus Thunderweight interactions. So we have a potential which is given by harmonic bonds between nearest neighbors. This models deviations from chemical equilibrium, plus Thunderweight interactions within each chain and between the chains. And we compute Thunderweight interactions either by using Lennard-Jones kind of potential in a pairwise approximation, or we solve the many-body Hamiltonian with the MBD method, which I've already described, and I think I don't have to go in much detail here. So we diagonalize a Hamiltonian corresponding to quantum harmonic oscillators, and we couple these two systems. So, and what we find is very striking. So if you use the standard pairwise approximation that most people use, then the adhesive stress decays very quickly, right? At 100 angstroms, so 10 nanometers, you pretty much, the stress already vanishes almost to zero. But if you do many-body dispersion, so you treat Thunderweight interactions in a fully many-body fashion, then the decay is much smaller, and it depends on the parameter that defines the overlap between the Gaussian wave functions of the oscillators, how much, how the stress decays. So there's a whole area here, and so you can go from here to there depending on the coupling parameter. And if you look at the highest limit of this curve, well, you are not so far away already from at least one of the experimental curves. Okay. Now, of course, what we have here is an approximate physical model, and we cannot do full quantum mechanical treatment of it because we have 40,000 atoms, and we have to relax the whole system, right? So we do full relaxation at each separation distance, right? So we fix the distance at one edge here, right? And we delaminate this structure, relaxing it at every different distance. Okay. So this is a very heavy calculation, even within this very, very approximate model for inter and intra-atomic interactions in this chain. And if you now want to understand why this non-locality happens, what you can do is you can compute the Hessian matrix of a system, which means that you compute the force on atom J as you displace atom I, because that's what dictates the long-range structure and deformations of the geometry of the system. If you do this with a pairwise model, well, basically everything is local, as you expect, because the Hessian matrix elements decays 1 over r to the 8, because it's a second derivative of a 1 over r to the 6 potential. But if you do the many-body dispersion calculation, you see that the Hessian matrix elements almost never decay, and they propagate to distances which are significantly larger than in a pairwise approximation. In fact, if you look at long distances between two atoms I and J, then the coefficient of the Hessian matrix is 3 to 5 orders of magnitude larger than the pairwise approximation. And that's because in a many-body picture, what interacts are not two atoms, but two fragments, two polarization fragments. And those polarization fragments can include 100 atoms. So that's why the coupling coefficients in the Hessian matrix really become giant, and they are responsible for this ultra-long range scaling of the adhesive force. Okay, so this is one example of ultra non-locality at the nanoscale and actually mesoscale. But actually, quantum mechanics can give you many more surprises. So here is another experiment which was published roughly at the same time, which shows a completely opposite behavior in a complex nanoscale structure. So in this case, what they do in this paper is measure the force with atomic force microscopy with a very thin tip here between the tip and a silicon surface or silicon surface with a single graphene on the top. And this is a nanoscale experiment. So the distance between the tip and the surface is from 3 to 20 nanometers. So my first experiment was macroscale, if you wish. This one is nanoscale. Okay? And here, what they observe is that once the graphene layer is put on top of the surface, the interaction between the tip and the underlying surface completely vanishes. So it's completely screened out by the surface. And this has been explained by actually a few people who will also give talks here, by Tim Gould and also by Alberto Ambrosetti in these two papers. And they call this a Faraday cage effect, because it resembles what you get in a metallic cage, right, where all the external fields cannot propagate. So in this case, they extended this model to electron correlation interactions, and they said, that graphene can actually act as a Faraday cage by removing interactions at most lowest frequencies, and hence it screens out the interaction not completely, but by 80 to 90%. So now let me join these two experiments with a third experiment. So this is under review now. And what we asked then, can we actually understand those two different extreme experiments? So one experiment was at the macro scale, another was at the nanoscale. And what you can do then is propose a different kind of experiment. So you have an underlying surface, and you have a macroscale tip. So you don't have macroscale cantilever, without any tip at the edge, right? So you really measure a macroscale force. You have to make a very specific setup to do this because you have to basically align the two samples. You have to withdraw this laser that measures the position of the cantilever on top of the surface. There's a lot of tricks you have to do, but this was done by this very talented postdoc, Pavlo Gordichuk. And then what you can do is you can grow several layers of graphene on top of this. It's a silicon surface, and you grow several layers of graphene from 1 to 6 to 12, and you can then go up to highly ordered pyrolytic graphene. And so what is interesting here is you have a macroscale measurement of a nanoscale structure, and you can do those measurements as a function of separation from nanometers to micrometers. So if you do those measurements at contact distance, where the tip enters contact with the underlying surface, then you get something like this. As a function of the number of layers, the force saturates, okay? And this is something you would expect from a standard calculation, right? As you increase the number of layers, the force should saturate eventually. However, the saturation is actually pretty slow, as you see. So if you do a DFT calculation with some pairwise potential, you would expect that by 2 or 3 layers, the force completely saturates. But here, you see that the force does really saturate at 2, 3 layers. You have to go up to at least 20 layers to see the saturation of the force. But the most exciting results are here. So here is the ratio between the force on n graphene layers divided by the force at HOPG, so fully, infinite, highly ordered pyrolytic graphene. So, and you do this for different separations. So for close separation, for 200 nanometer separations, and 500 nanometer separations. These are very, very large distances atomistically. And what you see is that HOPG, actually, at these large separations, do not give you the highest force. The highest force is obtained for a finite number of graphene layers on top of the surface. And in fact, the force on top of 20 layers can be 5 times larger than the force on top of HOPG, which is, quite surprising. And you see this much better here. So you see Pavlo, he's the one who really did those experiments. And so here are the actual full curves. So this is a separation in micrometers. This is the force. So here you have 1-layer graphene. This is all logarithmic scale. 2-layer graphene, 4-layer graphene. And then suddenly, HOPG is here. But 14, 17, and 21 layers is actually have much higher forces than HOPG. And the scaling law, another thing which is very surprising, the scaling law of the force is d to the minus 3 at HOPG, which you can get from some model. But the force actually decays faster for finite number of graphene layers. And nevertheless, although it decays faster, so d to the minus 4 is a larger denominator, or d to the 4 is a larger denominator, but the magnitude of the force is higher, which means that the coefficient is a running coupling parameter as a function of the distance. And that's because the finite number of layers of graphene polarizes in a nonlinear way. And you can explain it by a many-body model based on random phase approximation, which is, again, it's an approximate model. It's not a fully atomistic model, but you can make up a model that actually reproduces those results in a qualitative way. But it's not an atomistic model, okay? Because you cannot atomistically treat the systems which have millions of atoms, okay? So these 3 examples, I had the first example of ultra-long range scaling, had a second example of complete screening at the nanoscale, and a third example which integrates macroscale and nanoscale and tells you that you can get very non-trivial, novel effects in interfaces which integrate nanoscale in one dimension and macroscale measurement in another dimension. So you really see quantum mechanics with a macroscopic cantilever, which I think to me is very surprising, right? I would never have expected to see this before realizing those experiments. But the issue is the interpretation, the models that we have to do to interpret this are all extremely approximate. And of course, they are built on the experimental observations. We first have those experimental observations, and we build a model. It's not too hard. If you have a good postdoc that knows, quantum mechanics and knows model building, he can do this. But we would like to really go beyond and have more atomistic understanding of these effects and how this macroscale and nanoscale structures actually really interact with each other. Right? Okay. Are there any questions up to now?
Yes.
Yeah, sure.
So, does your model include the possibility of having a small charge transfer between a carbon and silicon?
So basically, the way we explain this behavior and why the multi-layered graphene never converges to HOPG is because when you grow graphene, there is always stronger decoupling than in HOPG because you have impurities and so on between the layers. And of course, the layers are not perfect, right? They are, bent and so on. And because of that, the effective coupling, the electronic coupling between the layers is much weaker than in HOPG. And that's what creates much stronger polarization outside of the surface, actually. So there are a few assumptions here, right? And so because of this decoupling, the charge transfer is not that important, actually. Of course, what can happen is that electrostatics might play a role, but it cannot play a role at such large distances because you have to integrate over 2 dimensions, and when you integrate over 2 dimensions, electrostatics decays always exponentially. So the only explanation for those power laws can be, so electrostatics can never give you these power laws, right?
Okay, so the charge transfer, even if it's there, it cannot.
Yeah. It could contribute to the polarization, so we don't claim quantitative results. In fact, at large distances, we cannot reproduce experiment, at really large distances. We can reproduce up to 100 nanometers or so, but with our model at 500 and micrometers, we cannot reproduce it. We have to introduce some other assumptions. Yeah. So the model is not completely predictive.
Yeah, Alexandre, I have a question about phonons. So when you delaminate ultra-thin films, there's a lot of relaxation on the film surface, which can change forces by an order of magnitude.
Right.
Did you account for these in the simulation?
So in the first example I showed, right, where we do this delamination, we do full relaxation, and in fact we also compute free energy in a harmonic approximation for the phonons, right? In this case, we didn't do it because this is already very hard to do the electronic part, but we did do measurements at different temperatures to see whether there is a strong effect, right? Because the phononic contribution at different temperatures would be very different. The change in the force at different temperatures was about 30%. And so we went from 200 to 350 K or so. So we assume that the phononic contribution is important, but it probably does not change qualitatively the result.
But and if somebody asked you to put error bars, like suppose I was the nature referee for that one, the first thing I would ask you is what are the error bars for the theory curve?
Oh, for the theory curve, yeah, it's pretty hard to say because the model is extremely approximate. So I wouldn't put my money on the theory model. I mean that's my main point. We see experimental results. We can explain them qualitatively, but the theory model is very approximate. In fact, one of the nature referees was very upset about the theory.
The experiment is right and the theory is wrong. I mean, that's my question. So because there can also be measurement error or whatever.
So the qualitative aspects of these measurements can only be So we have a minimal theory, which is a many-body theory, right? It's an RPA approximation with an effective dielectric function of each layer, right? Which we know very well, by the way, from first principles calculations. So the only way to qualitatively reproduce this is the simplest way to qualitatively reproduce this is by a simple theory. But then the quantitative aspects and the scaling with distance and so on, it's hard to say. So electrostatic cannot reproduce this. I mean, this is pretty certain. Okay, very good. Now, another example which I want to give to close this challenge section, let's say, is, these were experiments, but even in theory, right, when we compute larger systems and we want to know their binding energies, there are some outstanding challenges that we still have in the field. I talked a bit about this actually during the tutorial week. I would like to mention it again because to me this is still this challenge that remains unsolved. So, you know, in the quantum mechanics community that aims to extend QM methods to large systems, there are at least two different paradigms in terms of dynamical correlation. There is the quantum chemistry community, which, you know, builds their methods on Hartree-Fock and then puts correlation using coupled cluster or CI methods. And then there is the physics community that prefers a quantum Monte Carlo kind of approaches to solve the Schrödinger equation. And of course, all these different communities defend their methods to death. And in fact, gold standard is only gold standard calculation refers typically to coupled cluster, the single, double, and triple excitations. But if we do not have two completely different approaches that give us the same numbers, we cannot say, right, if one of those is accurate or not, right? So we need at least two standards, or hopefully three, right, to really know whether the calculations we do are accurate or not. And so Yasmin, who was a postdoc in my group a few years ago, right, we kind of said, okay, let us take a set of benchmark systems that people have been doing in the field and go to larger scales, for example, to this buckyball catcher, this is 150 atoms or so, and let's see whether coupled cluster, so the single, double, and triple excitations, and quantum Monte Carlo yield reproducible results. And they don't, right? So here is an example from this paper. So when you apply these two methods to benzene dimer, for example, this is a small, you know, aromatic dimer, then the results from QMC and coupled cluster are essentially the same, within 0.1 kcal per mole, which is a very small threshold. And so this means that they give the same results. But if you go to larger systems, so this buckyball catcher, two methods give difference, minimal difference of 8 kcal, maximal difference is 12 kcal, depending on how you include different convergence criteria and stochastic errors in quantum Monte Carlo. This is a huge discrepancy. So this is 12 orders of magnitude in terms of binding affinities at room temperature. So this is awful, right, this difference. And once again, these calculations were done by experts in each of the methods, by people who actually developed the methods. Okay, so they have their own codes that they've programmed, that they are sure that work correctly. And this went through many referees that also developed methods. And we don't know why there is such a big difference between these methods. And we all have our own theories, which I can tell you after the talk, right? But basically, even for such small systems, 150 atoms, we do not have reference data, right? We don't know what the reference should be. And so I think there's a lot of scope for method development and understanding of what the actual binding energies in large systems should be. This is even not a multi-reference system, right? I mean, this is organic molecules. They're supposedly single reference. If you look at the coupled cluster amplitudes, they are not too large, so Hartree-Fock determinant still has the largest, very, very high contribution. And so you would assume this is a single reference system, right? But you don't have the same binding energies from these two methods, right? Coupled cluster and QMC. Good. Okay, so, you know, given those differences and these challenges, I would like now to move and ask the question, well, can we build a systematic theory of quantum systems, of large quantum systems, starting from the most quantum system of all, which is the quantum field, or the vacuum field. Now, the vacuum field, right, is what creates the Coulomb potential in our electronic structure calculations, right? It's not a classical potential, it's a quantum potential, right? It comes from fluctuations in the field. The easiest way to understand it is looking at Maxwell's equations, right? If you solve Maxwell's equations, you put two sources, then you get a potential, which is actually also a retarded potential, it's frequency-dependent potential. And so in principle, before we even start to think about atoms and dimers and large structures, we should understand how to model correlations in the vacuum itself, right? And the vacuum itself, of course, has many different definitions. So if you follow different schools of thought on vacuum and field theory in general, you can define vacuum in different ways. For example, one definition is that vacuum is the when you take all matter and all fields out of vacuum, so it's really black and nothing happens, right? So it will look something like this, right? There's nothing in it, but of course this is it becomes black when we remove everything, and so what we have a background with all possible fluctuations, we average over them, and we get no density of fluctuations at every point. But of course, if you look instantaneously at the field, right, then it might look something like this, right? So this is, let's say, an artist's rendition. It's really actually many harmonic oscillators superposed, and the density of those fluctuations is here. So the orange ones is where you have higher density, the blue ones where you have lower density. If you average, it's 0, right? But because the field fluctuates at every point in time, you could have something like this, right? And so the question is, can we first understand those fluctuations? Can we have a model for those fluctuations? And what is the observable effects of those fluctuations, right? So can we build a more fundamental theory starting from the vacuum field? Now, of course, the quantum vacuum is not just a vanity, right? It has actual observable effects. And we know quite a bit about those observable effects. The first thing we know is, for example, lump shift in hydrogen atoms. So this is an effect that goes beyond the Schrödinger and Dirac equation, right? So basically every electron, so you have a nucleus here, and every electron fluctuates, right, because it interacts with quantum vacuum. So it produces and absorbs virtual photons while it's oscillating with respect to the nucleus. And you can build a very simple model for this, right? So basically what you say is that the effective potential that the electron feels from the nucleus is not just the Coulomb potential, but it's a displaced Coulomb potential. And the displacement is given by this absorption and emission of virtual photons from the electron. And it turns out that in order to get this delta R parameter here, it scales with what is known as the fine structure constant, which is the dimensionless constant of nature, which is 1 over 137.35999, and so on, right? It's been measured to about 10 digits right now. So the lump shift is in reality defined as a shift between the two S and two P states. So the P states do not shift because they have a node at the nucleus, but the two S states do shift because they are not 0 at the nucleus. And the lump shift, this energy shift between 2p and 2s states, is given by this expression. So you have a rest energy of the electron, me is t squared, multiplied by the fine structure constant to the fifth power. And of course, the fine structure constant is a small number, right? Hence, the shift is very small in terms of chemistry. It's 10 to the minus 4 kcal per mole, right? We said that chemical accuracy that we want to have for our quantum mechanical system is 1 kcal per mole, so this is 4 orders of magnitude smaller. However, this shift is only for one electron in a hydrogen atom, right? We don't know what will happen if you have 10 to the 4 electrons, say, in a protein. Will this lump shift still be so small, or do you have to actually scale it up by the number of electrons in your system, right? No one has done those calculations for a protein or a nanostructure, right? So we don't actually know. A second effect, which is also quite often mentioned, the observable effect of quantum vacuum, is so-called the Aharonov-Bohm effect. And here, what you have is a typical double slit experiment, right? So you have an electron source, say, you have a screen, right, with two openings, double slit screen, and you get a diffraction pattern, right? But then you introduce a solenoid outside, right, on the other side of the screen. So in principle, the electrons never see the solenoid, at least they do not see the field, the magnetic field of the solenoid, because the magnetic field is confined within the solenoid. Outside is 0, right? But nevertheless, when you measure the diffraction pattern, you get a shifted pattern. And that's what typically people say, that the Aharonov-Bohm effect tells you that the fields, the electric and magnetic fields, are actually not the important quantities, they are local quantities, but what is important are actually the potentials, the electric potential, the scalar potential, and the vector potential. Right? So there are several interpretations, and of course this also implies that gauge fields that propagate the interactions are actually non-local. The third effect that is often mentioned as evidence for quantum vacuum is the Casimir force. So here you have two plates, right? And because those plates impose boundary conditions on the electromagnetic plane waves, right? Then there is an effective interaction, which is attractive interaction, that depends on the distance between the two planes, right? Because the density of those electromagnetic modes between the planes and outside of the planes is different. And so if you subtract the energy between two planes at distance d and at infinity, you get an effective interactions. Now, of course, in the context of chemistry and material science, we typically do not think of Casimir interactions, but we think of Thunderweight interactions. But the physical picture behind Thunderweight interactions is exactly the same as Casimir interactions. You just assume that the interaction between electrons happens with a Coulomb potential, so it's not really retarded interaction. And of course, we know that Thunderweight interactions is ubiquitous everywhere. Now, of course, while they are so important, I think has been nicely summarized by Mark Ratner, who is a prominent computational theoretical chemist in Northwestern, just retired actually. I think he said this nice phrase, right, that today in 21st century, we really need to care about intermolecular interactions, and for that reason, a lot of chemistry has really moved to understanding supramolecular systems and material science, and that's where you cannot do anything without proper description of intermolecular interactions. Okay, so let me try to connect these Thunderweight interactions then and the quantum vacuum field. So the textbook picture goes like this. So you have two atoms, A and B, and they are spherical, which means that they have no multiple moments. If you integrate their density, all the multiple moments are zero. And so in classical mechanics, there is no interaction between A and B. However, both A and B interact with the quantum vacuum, right? And because of that, there is an instantaneous polarization at each point in time. Or you can reformulate it in frequency space if you wish. And so this means that there is a bit more density on this left side of the atom than on the right side of the atom. And so this creates effective dipoles and higher order multipoles. This happens for atom A and this happens for atom B. And then when you integrate over the interactions between those multipoles, you get an effective interaction energy that scales as a function of R, the distance between the atoms. If you want to compute this, the easiest approach is to use perturbation theory. And I gave this tutorial already in the first week where I derived these terms, right? So in second order perturbation theory, you get this interaction energy, which scales as r to the minus 6. The simplest way to understand r to the minus 6 is you have r to the minus 3 dipole forming here, induced dipole forming here, r to the minus 3 induced dipole forming there, and they correlate. In second order, you get r to the minus 6, okay? And the important thing, the scaling parameter that defines the interaction is this 6 coefficient, which you can compute from this so-called Casimir-Polder integral, which depends on the frequency-dependent polarizabilities, which is nothing else but a description of how your atom fluctuates as a function of time, Fourier transformed to frequency space, or to imaginary frequency space, right? And so these things you can compute from first principles calculations, and once you have computed those functions, they are monotonic function of imaginary frequency, you get a 6 coefficient. Now, in principle, we can derive exactly the same picture from quantum electrodynamics as well. So what this means is that we will not only quantize the matter degrees of freedom, or the atomic degrees of freedom, but also quantize the field degrees of freedom. And then we have to do fourth order perturbation theory in terms of fluctuations of the electrons, fluctuations of the vacuum. We integrate everything, and we will get exactly the same expression, right? So by doing this, you could say, well, I don't gain anything from QED, right? I get exactly the same expression as in second-order perturbation theory in quantum mechanics, but I would like to demonstrate in the next few slides that actually this picture QED picture is more productive and it gives you a bit more insight. Okay, so what we really want to do, of course, is we don't only want to understand what happens at large distances. So the second-order perturbation theory you can only do when the interaction is small, right? That's where perturbation theory converges. When interaction is large, for example, the two atoms are at the equilibrium position, then we cannot do perturbation theory, right? But what we would really like to do is to understand how stability of matter emerges from its electronic properties. And so in reality, right, the two atoms, they start far away, they come closer to each other, and at some point, the antisymmetry of the wave function becomes important. This introduces Pauli repulsion, right? And the two atoms will form an equilibrium dimer, AB. And the parameter of the equilibrium dimer, the geometrical parameter, is defined by so-called van der Waals radius. Van der Waals radius is nothing else but half of the equilibrium distance between two closed shell atoms. This is something you can measure in experiment, right, from scattering cross-sections. You can compute this in your favorite quantum chemistry package, and so on. And here are the examples of the full binding energy curves that you get as a function of equilibrium, as a function of separation between different noble gas atoms. Helium-helium, neon-neon, krypton-krypton, argon-argon, xenon-xenon. You see that all these curves are sort of similar, but the equilibrium distance is different depending on the van der Waals radius of each. So the question that I'm going to ask, and to basically connect this to quantum electrodynamics, is can we establish a relation between a geometric property, the van der Waals radius, and an electronic property, the dipole polarizability of an atom. So the dipole polarizability is what I had in my van der Waals interaction, right? This defines the long-range interaction between two atoms. So we can do this first in classical mechanics. This is, textbook exercise. So you assume that the atom is a point charge, and the electronic density is distributed uniformly within a sphere, which is defined by a radius RA. And when you apply external field to it, then the positive charge will displace to the negative side of the external field, negative charge will displace towards the positive side of the electric field, and you can define a force balance equation, which in the end gives you this result, that the polarizability is van der Waals radius to the third power. So it's just proportional, or just equal to the volume of an atom. Okay? This is a trivial result. You can find this in any textbook. But can we actually do this in quantum mechanics? So in order to do this in quantum mechanics, we need a proper quantum model. This homogeneous density model doesn't work. It's a classical model. So in order to do this in quantum mechanics, the simplest model that approximates the response of atoms is the quantum Drude oscillator model. It's a model that describes an atom by three parameters, by an effective charge, an effective mass, and oscillation frequency. And that's the polarizability that depends on these three parameters. We can parameterize any atom by this QDO model. You just need three parameters of a real atom, for example, polarizability and two dispersion coefficients. And then you have two atoms, you couple all your nuclei and your Drude particles, your effective Drude particles by Coulomb potentials, and then you can solve this system quantum mechanically. If you do this, then one can do a multipolar expansion of the potential. So you can compute the force, the attraction force, the van der Waals attraction force. This is r to the minus 7 multiplied by this prefactor. And in addition, in order to get the Pauli repulsion, you can assume that these two atoms are indistinguishable bosons instead of electrons, so they are bosonic systems. But you can make them indistinguishable because they have the same parameters. And you can write the wave function of this dimer as a permanent, which is not a determinant, it's a permanent. You just change the sign, right, of the wave function. And then you can also derive the repulsive energy in the same way. And then you can make basically a force balance. So the attractive force is equal to the repulsive force. And what you get then, surprisingly, is that the polarizability now does not scale as van der Waals radius to the third power, but van der Waals radius to the 7th power, which is qualitatively different scaling, right, in quantum mechanics compared to the classical mechanics. Now you can check if this actually works. So you take different noble gas atoms from helium to xenon. Okay, you take the van der Waals radii from experiment, you take the atomic polarizabilities from reference calculations, and then you compute two things. You compute the ratio between the van der Waals radius and polarizability to 1/7, right, just using the scaling law, or you do this in a quantum Judo oscillator model. And something surprising happens. So in the quantum Judo oscillator model, the coupling coefficient, so the coefficient that goes here, is not very different, but it does run, right? So for example, it changes from 2.28 to 2.56. But if you now take the same scaling relation and apply it to real atoms, this coefficient seems to be a constant. And that's a big surprise because in a model, in this quantum Judo oscillator model, you obtain that the coefficient of the scaling law is not constant. But for real atoms, it is a constant. And typically in physics, you always have another opposite situation. You make a model, and in this model, you have some conservation law, some symmetry. But in real systems, you don't have that symmetry because real systems are more complicated. In this case, we have the opposite situation. Real systems are easier, so real atoms are somehow simpler than the model, the quantum Judo oscillator model, which is quite a big surprise. Now, is this coefficient really a constant? Well, here is the result. So here is the scaling of the van der Waals radius with respect to the van der Waals radius computed from the polarizability, and it's perfect. It really gives you an error of 0.5%, and of course, the van der Waals radii are not exact, so they have some error in them. Instead, if you use the classical scaling law, the R van der Waals to the 3rd power, then you get errors which are 20% or 30%. Okay, so this quantum mechanical scaling law really works with a constant coefficient. Okay.
Is it the perturbation theory the next term separated by several orders so that
the multipolar term, or yeah, so the multipolar terms are important, and you also get scaling laws for the multipolar terms as well. So it seems that this expansion of the full Coulomb potential in multiple orders give you different scaling laws for each multipolar term, basically. Yeah. Yeah. So the dipole approximation actually is, of course, is not exact at equilibrium. It is, it gives you 60% of the binding energy, but nevertheless, somehow the scaling law you can also separate in a multipolar expansion, and it works. Okay, so this formula not only works for noble gases, it actually works for the whole periodic table. Now, for the whole periodic table, the van der Waals radii are, of course, statistically defined only because people measure crystal structures, and then they take close bonded van der Waals distances between atoms, and then they statistically define an effective van der Waals radius. So for noble gases, this definition is very simple. I have 50, right? Yeah. We started a bit late, no?
Okay.
I need maybe 3-4 minutes. Okay, good. Right. So this really works, right? With an error of 3% and with relative deviation of just 0.6%. So this scaling law really seems to be reality. Okay, so if you compare now this quantum picture versus classical picture, right, that we realize that we have a really qualitative difference. So in a classical picture, the scaling is proportional to the volume. In a quantum picture, it's proportional to this 7th power. So now the question is, what is in this constant? So I can rewrite now the scaling law of polarizability with respect to van der Waals radius in its full glory, restoring all the dimensionality, right? And actually, of course, you see that the scaling dimensionally has to be the same. So you have a 7th power of the distance. So you have to divide it by Bohr's radius to the 4th power. You have 4 pi epsilon 0. And then you get this constant. So I call this Ferdorow's constant because Dima Ferdorov was the guy who actually first obtained this constant in my group. And the question is, well, what is 2.54? Is there some factors of 2 or pi, or where does it come from? And the way to obtain this is basically making an analogy between the classical scaling law, which is given like this, between polarizability and classical radius, and the quantum scaling law. If you look at them, you realize that they have to intersect at some point, which means that there exists some critical radius at which these two radii basically coincide, and of course there will be some critical value of polarizability where they coincide. If you impose this and you obtain the effective radius, you get this result. So the critical polarizability is equal to 133.5 plus minus 5.5, and the critical radius is here. And if you look at this value, you realize that it looks very much like what I already had in the beginning of my talk, the inverse of the fine structure constant. Now this, at the moment, I'm giving you a numerical proof. You can say it's numerology, but I don't have time. But in this paper, we actually explain why this formula actually makes sense. So you really have a relation between a geometrical parameter of an atom and an electronic parameter through something that depends on the quantum electrodynamic field, the fine structure constant, which is a dimensionless constant of nature. Basically, first of all, it works really. So you can obtain the fine structure constant by just taking the atomic Thunderweight radii and polarizabilities. You compute this from this formula, and you see that it's pretty close to the exact value of the fine structure constant. And the fact that this formula works, as we show in this paper, in a bit heuristic way, is that the Thunderweight radius is really a radius of an atom that is endowed by the quantum electrodynamic field. So it's an effective radius of a cloud of virtual photons that the atom actually generates in a field. And so here is the relation between the quantum mechanics and quantum electrodynamics that I was really telling you. This means that typically the fine structure constant describes just the tail of the elephant, right? So people typically use the fine structure constant to compute perturbative terms, how a quantum field influences an atom. And what we show is that the fine structure constant can actually describe the whole animal, right? Because it is involved in a relation between a geometrical and electronic property of all atoms in the periodic table. So it's a new scaling law in its own right that comes out of the quantum electrodynamics. Of course, my final two slides is we want to go beyond these two atoms, right? We need to go to real systems. And what we really want to do, what I'm pretty convinced about, is that perturbative treatment of the field is insufficient. So we know very well, for example, how to take a real biological system and model it as a collection of quantum harmonic oscillators. This is given by this Hamiltonian here, which is a very general Hamiltonian for a set of harmonic oscillators. But what we really want to do is then go to QED, right, and introduce field degrees of freedom. So this is creation annihilation operators of the vacuum state, which we heard about a lot in the tutorial week. And this is the coupling between the transition dipole moments of your oscillators and the vector potential of the field. And we would like to solve this Hamiltonian beyond perturbation theory, because we are sure that in order to really obtain this scaling law that I've presented from first principles of quantum electrodynamics, we need a non-perturbative treatment of such kind of Hamiltonians. And I'm sure that we will not only obtain this scaling law, but we can obtain many more scaling laws for large molecular systems if we are able to do non-perturbative treatment of this Hamiltonian. Okay? This will lead to many other things, I think. We will not only, if we have this non-perturbative QED treatment of molecular interactions, I really like to see whether we can compute lamp shifts of plasmon modes in complex molecules. They can generate effects which I think go beyond energy of thermal fluctuations. We can classify molecular interactions in the presence of all different fields, and also compute potentials for complex systems, right, as a function of the distance that include retardation effects, quantum mechanical effects, and so on. And I think there will be quite some work actually in this workshop also trying to go in this direction. So with that, thank you very much for your attention.